Great. Hello, everyone. Thank you so much for joining us today. My name is Isaac Wink. I'm the Research Data Librarian here at UK Libraries, and I'm very excited to be presenting part 4 of the Medical Center Library's Horrors of Bad Research series on data disasters, how to avoid horror stories in data management. So a little bit about myself. As the research data librarian for UK Libraries, my role is to support researchers in data management and sharing activities across the research data lifecycle. So a couple of different discrete areas where I can help you include writing data management and sharing plans. Those can be both for federal funders like the NIH and the NSF, or they can also just be a way of writing a data management plan to serve as a guide for your research team as well. While research is ongoing, I can help with developing data documentation practices for your team. So that can include developing file naming conventions, README files, data dictionaries, and we're going to go into a couple of those strategies today, but if you want to learn more about them, sign up to have a conversation with me. And then at the end of the process, I can work with you on sharing and getting credit for your data by making sure that that data is well curated and that it's shared in a repository where other people can easily find it and where it's going to persist. Laura shared the link in the chat, both to the slides for today, as well as to our guide on research data at UK Libraries. So please check that out if you'd like to learn more about any of these topics or anything that I cover here today. So I always like to get started with these sessions by just describing a little bit of what data management is, because data management can really be a big all-encompassing term. And in that situation, I find that it can sort of mean everything and nothing to everyone all at once. So this is my preferred definition of data management, and it comes from another data services librarian, Kristen Briney. Data management is the compilation of many small practices that make your data easier to find, easier to understand, less likely to be lost, and more likely to be usable during a project or 10 years later. And the thing that I really like about this definition of data management is it shows how data management practices are modular and individual tasks that compile into something greater than the sum of their parts. And what that means as well is that all of us in our research are already engaging in data management in a variety of ways. Maybe we do have some intentional way that we're naming our files, but maybe we're not thinking about data documentation or data backups, for example. So I always like to encourage researchers to take stock of the practices that they're already conducting to make sure that their data is well managed, and then try to encourage them to consider some new ones that they can add on to make what they're doing better in a modular fashion, rather than thinking of data management as being an all or nothing proposition. So when it comes to data management, one of the big reasons to conduct it at all stages of the research lifecycle is to avoid data disasters. And that's what we're going to be focusing on today. There are a lot of different consequences of poor data management at different stages. One of the most significant and familiar to a lot of researchers is that poor data management can harm the verifiability and reproducibility of published research, which can then end up leading to retractions. Um, we know that a number of article retractions, sometimes those are due to outright data falsification or some other intentional malfeasance on the part of a researcher. But unfortunately, there are a lot of cases of honest researchers who really are trying to stand by their findings, but who haven't organized things well. And so when they go back to try to answer questions that others may have about their findings, they aren't able to answer them because they can't find the original data, or perhaps they can't verify their methodology or the analysis that they use there. So even honest researchers, of which we know there are many, many, I'm sure all of you are honest researchers, even they need to make sure that they're thinking about data management as a way of protecting against issues with the verifiability of their research. Another problem can be data loss that leads to, or poor data management leading to catastrophic data loss if that data isn't backed up properly. This is a problem that I think a lot of us sort of tend to outsource to third-party software that we're using, whether that's something like OneDrive or another cloud-based service for holding our data, or maybe we put it on the department that we're in and sort of make assumptions about how that data is being backed up. And on a day-to-day basis, that often works out pretty well for a lot of people until it doesn't, and then it really can be a true catastrophe. One example of this happening was with the platform and research tool Deduce, which is used for qualitative research and a lot of mixed method studies. In 2014, they experienced, really just due to bad luck, a pretty catastrophic situation in which both the main primary version of their user data went down at the same time that their backup data went down as well. So in that case, Deduce was able to recover user data, but it was a process that took several weeks and months and then ended up delaying people's ability to participate and conduct research. And I don't say that to pick on any, individual software here, but really just to encourage everyone to think about what tools they're trusting to store their data well, and spend some time thinking about how they can protect against those. Another issue that can come up with poor data management is increasing the risk of data breaches or misuse of data, or the leakage of personally identifiable information in published data. One recent example of this comes from the world of libraries and library research, where there was an article that was published in a journal, Code for Lib, that included Microsoft Power BI files as supplementary files to the article, which was on how to build user dashboards for a library. And those Power BI files weren't properly vetted before they were shared as part of this article, and actually ended up including patron data, including information about which books patrons had checked out. So that was eventually taken down, but it was a pretty serious breach in terms of information that should never have been made public in that way. And good data curation practices are a vital step to make sure that personally identifiable information isn't accessible in that way when data is shared. Now, all of these factors brought together can cause long-term damage to the credibility of both individual researchers, research teams, and then institutions as a whole as well. And those reputations can be difficult to restore once they're harmed. And you don't want to find yourself in a position where you are the star of your very own data management horror movie. And so that's going to be the subject of this Horrors of Bad Research session for today. And in order to do that, we're going to dive into some of the data horror movie classics. We're going to tackle 4 of those in particular: Data Lost in Cyberspace, Zombie Research Data Policies, Data Armageddon, and Attack of the Dataset Clones. For each of these, we'll cover the classic trope that you can expect to find when you're watching, or hopefully not, but perhaps living that movie. We'll look through an example plot to see the actions that lead to the specific horror. And then finally, we'll look at some of the strategies and tools that are available to you to make sure that you make it through the movie alive. So we'll get started with our first movie, Lost in Cyberspace. So when you're collecting large amounts of data, particularly when you're part of a research team, it can be difficult to keep track of all of the files that you have and all of the data contained within them, particularly if you aren't organizing those files in a consistent and intentional way. As I said, this can be a compounded problem on a research team as well, where a lot of different people are touching, analyzing, working with, cleaning that data on a regular basis. And it can easily lead to a situation in which you've lost track of your files, or maybe even lost the files entirely. Even in situations where you are able to recover those, figure out where they were, if you've got a file that you haven't been able to access, then suddenly do find again, then you might have a lot of unanswered questions about it, such as, does this represent raw data or data that's been cleaned or processed in some way? What research site or trial is it associated with, for example? And so all of those mean that even if data can eventually be located, losing data in the first place can do a lot to slow down and even harm your research long term. So one of the biggest issues when it comes to losing data files is just a lack of clear and consistent file names. If you don't have good names for your files, then it's very difficult to be able to tell at a glance what's contained within them, or even what version of the file you're working with. If any of you are familiar with the webcomic XKCD, this is one of my favorite excerpts from it. In this case, it's looking at a downloads folder. I'm sure many of us may shamefully have downloads folders that look something like this. But we may also see folders associated with particular research projects start to look like this as well. We'll have multiple different versions of the same file, and we don't necessarily keep track of which one is the most recent version or what changes have been made between those. And the best way to make sure that you're protecting your files and keeping them from getting lost in this way and harming your research is by developing a file naming convention. And that's the tool that we have to get out of this particular horror movie. So a file naming convention at base is a consistently applied set of rules for naming files with contextually important information. And I say contextually important because the file naming convention that works for one research project, lab, whatever else, may not necessarily be the best for every other case. What's important is that once decided upon, a file naming convention is used consistently across the universe of files that it applies to. And there are three basic rules of thumb that I recommend when you're thinking about how to develop a file naming convention. The first is to make the file names descriptive. So highlight whatever information is contextually important about that file and will help you distinguish it from others that maybe look similar in terms of their data structure or even have similar names in other ways. But the name should be a method of being able to easily match the name of the file to its contents. Additionally, you want the names to be somewhat brief. I've seen some people who try to cram a lot of different information into a file name. And while it can be good to be descriptive, if your file name is running on for over 100 characters, then you're never actually going to be able to see the full name when you're going to that file on your file explorer on your computer. And if you're working with those files programmatically in any way, then it can be tedious to have to write out names that are that long. So the rule of thumb in terms of briefness is to keep your file names to about 32 characters long, which is about the length of the File Explorer window. Make sure that you can see all of that information. One way to keep those names brief is to use documentations where they're appropriate. Just make sure that those abbreviations are documented somewhere so that you and other members of your research team are able to revisit them later on. And then finally, make sure that your naming conventions are simple by sticking to numbers, letters, and underscores for the most part as a way of writing those names. In particular, avoid special characters like question marks, pound symbols, at signs, or slashes, because a lot of those are special characters in computer operating systems. And then as a result, can lead to errors when a computer tries reading the files that you have. Even if it may work on your computer, if you're sharing those files with a collaborator, they may run into errors there. If you want to get started with your own file naming convention, Laura has shared in the chat a link to a file naming convention worksheet. This worksheet goes through a list of questions about the data that you want to make the convention for. That's a way for you to start coming up with some ideas of what information is going to be contextually descriptive here and help you tell these files apart. And then at the end, it provides some recommendations on how you can string those together to write your own to come up with your own convention. So I recommend taking a look at that, not necessarily as a prescriptive thing where you need to be answering every single one of those questions. I recommend treating them more like recommendations, things to consider, maybe a new perspective on your data that you might not have had previously. One example of what this can look like in practice is the file naming convention I've written up on the left here for a hypothetical study that's looking at pollutants that are being measured in different cities. So here we have a file naming convention with three parts to it. We have the date of data collection written in the format of year, month, and then day. One advantage of this is that, while in the US, we are more accustomed to a date system that starts with month and then day and then year. In a lot of other parts of the world, the convention is to write first date and then month and then year. And using this convention that starts with year is a good way of avoiding ambiguity, especially when you're working with international collaborators, as a way of making sure that everyone understands what that integer string corresponds to for each date. The next part of this file naming convention is the city where data was collected. So this is just the piece that would be contextually important when we're thinking about the file naming convention for a study of pollutants in different cities. And then finally, the last piece of information here is the pollutant that's being measured with their abbreviations. Here I've written out what just a couple of those abbreviations could be using atomic symbols. So for example, PB for lead or CO for carbon monoxide. What's most important about these abbreviations is that they're documented here. And this is information that I would want to include if I were using this file naming convention as a way to make sure that myself in the future and other members of the research team can tell what those abbreviations mean. Now, one last thing I want to emphasize on file naming conventions is that they can be adapted based on what makes the most sense for your own research. And while there are some best practices in terms of consistency, there's not really one file naming convention that's objectively better than others. And as an example of this, I've shown how we can apply this file naming convention from the previous slide in a couple of different ways. When working with our data, we find that we're often sorting data by the date of collection, then maybe that would be the piece of metadata that we want to start these file names with so that we can more easily sort our data by date of collection. Conversely, maybe the way that we organize it is much more around city rather than individual date. We could put that information at the start of each file name instead as a way of making it easier to sort in that direction. The important thing when it comes to file naming conventions really is just to make sure that you are consistently applying whatever rules it is that you've set. So before we move on to our next movie, I'll just mention that there will be time for questions at the end. But in addition, if you have any on something specific that I mentioned and you just want to see it addressed right away, feel free to drop it in the chat, and I'll pause at the end of each of these sections to address anything that's there as well. So the next trope that we're going to be looking at are what I call zombie policies. And this comes from from the practice that research teams sometimes have of thinking a lot about data management policies at the beginning of the research process. Maybe they develop a file naming convention like the one that we just discussed. Maybe they have documentation like README files or data dictionaries or other organization rules for how all of the research data is going to be tracked. All of that information can't be something that's just discussed once at an early meeting during the research process and then never brought up again. One potential consequence if those things aren't discussed and followed up on and audited over time with members of the research team is that you'll have policies that may be written down in a folder somewhere in your research files, but aren't actually being implemented. No one has actually gone and checked that document. People aren't using it when they create new data files. And the result is that because there's no follow through, you have policies that aren't maintained, they aren't known to new members of the research group, and as a result, they aren't effective. So I think of these as zombie policies because they're kind of alive and dead at the same time. They're there officially, someone could go and find them perhaps, but in practice, it's not a part of the culture set by that research team to actually use them. And then this, in a way, can end up being more of a hindrance than not having policies at all, because you've got something that is sort of officially recorded there, but it's confusing for new members of the research team to know whether or not they're supposed to follow it or how it is that they're supposed to respond to it. So one example of how this might play out is consider a researcher who is starting a new investigation, maybe the one on city pollutants that we were just looking at, and develops the file naming convention that we just discussed. And they've got a very pretty way of organizing all of those files. They keep them all collected in a raw data file or raw data folder on their shared drive. And that's how researchers are accessing that data for analysis. That might work out really well when research first starts, But let's say that over time, that investigator and other members of the research team aren't really keeping up on those policies. And critically, when they're onboarding new research assistants or other members of the team, they don't reference or discuss that file naming convention at all. They assume that people will just sort of see it and understand what's going on and follow it. That can result in data that goes from this very neat and tidy picture on the left to one that looks more like this version on the right, where we have a lot of different members of the research team who are all organizing things differently. Maybe one member is trying to group things based on experiment and put all of the associated data in a folder for that. Maybe other members are grouping just all of the data that they collect since they're working with it the most, and they figure they'll just be able to explain it to anyone when they need to get access to those files. But then they're just using their own file naming convention on it, and there's no way to sort of consistently tell what's going on with all of those files. Now, these sorts of zombie policies, as I call them, can really be a trickier problem to solve than something like data organization when you're an individual researcher. Because in many ways, these are problems that come not from technology or not from organization, but research culture. And the signals that the PI or other research lead has sent to other members of the team on the value that is placed on this kind of organization and whether or not it's something that's followed up on and discussed later on down the line. So that means that the solutions to this problem are a lot more multifaceted than something just like, developing a file naming convention or other data documentation practices. That documentation can be really essential to have, but it's just as crucial to make sure that that information is disseminated to every member of the research team. One way to do that is when you're planning your data management policies, don't just think about what will our file naming convention, for example, be, but think about how are other people going to be able to access this. That means that that policy needs to be recorded somewhere. It needs to be relatively easy to follow and implement, and it needs to be easy to find. That can be including a special folder in your research with your research data specifically for documentation that people can review. It can also be something much more manual, like just writing your file naming convention on a Post-it note and then having that be available at the site of data collection if you're working in a lab, for example, so that it's easier for people when they're collecting data and entering new files to have that naming convention right at their fingertips and be able to implement it right away. Additionally, make sure that any documentation practices you develop are part of your research group's onboarding process so that new members of the team are actually explicitly introduced to these rather than just assuming that it's something that they're going to absorb over time. Another part of that is to make sure that you invite any questions about the policy, particularly for some students who may, not want to rock the boat or be afraid of asking questions or not being sure of how exactly to do something. It's much better to have people feel comfortable asking those questions and clear up any confusion at the start of the process rather than trying to correct errors later on as they come. And speaking of that, even if you've got a process that is well recorded and introduced to people as they join the research team, make sure that you or a designated member of your team are also regularly reviewing your files, conducting an audit of sorts for any data management issues that you see. The level of rigor that you want to put into this can sort of vary. Maybe it's just scanning the file names to make sure that everything is matching that convention. Maybe if you have more specific rules around data collection, it's actually going into the files themselves and checking for issues. The goal here is to catch any issues before they spread. Much like, in every horror movie, you try catching the zombie virus before it spreads to everybody else, and then, that always fails because otherwise there would be no movie. But we don't want that happening with your research. So one tool for being able to actually implement some of these is a data management for research teams checklist, which Laura just shared in the chat. I like that as a resource for if you're already engaging in a research process, go through and just sort of use that as a checklist to see what you're already doing and then maybe figure out what policies you need to change or adopt. And it can also be a good guide during the planning stage to figure out, to look through and think, hey, we don't have someone playing the role of data auditor here. Maybe that's a role that we should explicitly assign to someone. So much like the file naming convention, I recommend that as something that you can look at, get a sense of whether or not it's useful to the processes that you're engaged in, and just sort of see your data in a new way. And before we move on, I'll pause again briefly, just in case anyone wants to drop a question in the chat. All right. So our third movie is Data Armageddon. So this is addressing catastrophic data loss, by which I mean typically a hardware failure, but sometimes just an accidental deletion or a computer virus that leads to crucial files being lost in a permanent way, or even when it's not necessarily permanent, in a way that impedes research, sets you back several weeks or a month. Um, Now, data backups are one of those areas where I think we often outsource thinking about how our data is being protected to whatever tools it is that we're using. Maybe that's OneDrive, maybe that's departmental IT, maybe that's whatever service we're using for data collection. And there have been major improvements in a lot of data protection there. There's a lot more redundancy in data that in user data that's collected, but that doesn't necessarily mean that that should be taken for granted. One very common example of this is research data that might be collected and shared in OneDrive or Google Drive or some other cloud-based setting associated with someone's UK credentials. What sometimes happens is someone who's not staying on the research project long term, so a graduate student or a postdoc, for example, might have been the person who set all of those files and folders up in the first place. When they leave and their UK account gets deleted, that will sometimes result in their associated files on the cloud being deleted as well. So if the PI isn't the administrative owner of those files, then that can lead to those being deleted. And while there are options for recovering those, it's better not to have to engage with those processes if you don't have to, if you can do something simple like make sure that the PI is the administrative owner of files. When it comes to hardware failures, though, these are often really not a problem. I think we don't think about them all that often until suddenly they are, and then they are very much a five-alarm fire. And one example of this actually comes from UK itself. A couple years ago, over winter break, I think between Christmas and New Year's, there was a pipe that burst in Anderson Tower, and it flooded the server room of the College of Engineering and caused critical damage to 10 servers. So damaged a lot of research data and other data that was stored on those servers. And what was worse about this was because it was over winter break, this wasn't discovered for several days. So there was massive freezing in the room as well, which made it more difficult to recover that data. Um, Now, in this case, it was recoverable because the College of Engineering had partnered with UK ITS with their data protection service to make backups of that data repeatedly on third-party space. So even though those servers themselves did fail, that meant that there was no permanent data loss, but it did take a lot of staff time and hours to recover that data, and it did sort of set things back. There's a very interesting piece in UK Now, or however you'd like to pronounce that, in which UK ITS talks about their process for that. And I really do consider it a heroic story in a lot of ways, but it's also one that preferably researchers would rather not have to go through or have to think about. So the golden rule for thinking about protecting your data is to back up your data using what's known as the 3-2-1 rule. And this is a handy device for remembering to have 3 copies of your data on 2 different types of storage media with at least 1 copy of that data stored offsite. So you might have multiple copies of your data stored perhaps on a local work machine, but then also maybe stored separately on a cloud or other software service. And maybe if it's truly essential data, you're making sure that it's actually stored on multiple local machines or on an external hard drive, for example. An external hard drive would be one of those examples of a different type of storage media than something like your computer's own hard drive or something like USB drives or server storage access through a cloud or something like that. And then finally, you want to think about having at least one copy of your data stored offsite to be able to deal with any physical disasters, a fire in the workspace, a flood followed by a freeze, similar to the example with the College of Engineering. That's a way of making sure that if something does sort of go wrong physically with your data, you do have a copy in another location that you're able to access and restore it from as well. So when you think about the different media options for storing your data, there are a few different ones. One is personal computers, by which I mean not, the one that's not associated with work, but a laptop or, the hard drive associated with your workstation. Then you can also think about using an external hard drive. There are a number of different software that make it easy to run regular backups of files on your computer, and you can subset them to only copy specific ones. So you can make sure you're storing copies of your data, but not other files on your computer, for example. You can also use local servers. A lot of different IT departments at UK make it easy to access shared network drives as a way of being able to save your data both to your own personal machine as well as have a backup on departmental servers as well. And then finally, if you have really large amounts of data that you want to make sure you're preserving, but you don't necessarily need to access on a daily or weekly, any sort of regular basis, another option to consider is magnetic tape storage. It feels kind of obsolete, but it actually remains one of the most efficient means of data storage. The only problem is that it's kind of cumbersome to read from those magnetic tape drives once the data is backed up to it, but there are a number of programs, including one that UK is enrolled in, to have offsite magnetic tape store. I believe Oklahoma State University. So that's a way of making sure that you are having a copy of your data that's well offsite, well away from University of Kentucky, but would be an option for you to access your data if you need to later on. And I'll mention that those last couple of options for both local servers and magnetic tape drives, those are things that you can discuss with UK Center for Computational Sciences if you'd like to set up either of those options. Using a personal work machine or external hard drives are things that you can discuss with your local departmental IT as well. Some storage media that you should avoid backing things up to are USB flash drives in particular. Flash drives can be good for relatively quick data quick data transfer when you have something that you need to get from one machine to another. But flash storage is less resilient than other forms of storage, such as solid state hard drives. And that means that it's more likely to degrade over time. So don't think that you can save your data files to a flash drive, throw that in a desk drawer somewhere, and then be able to access that, 5, 10 years in the future. Hopefully it will still work, but it's better not to depend on that just in case that degradation does happen. And then additionally, make sure that you're avoiding obsolete media as well. So some people do still like to store data on CDs. That can be fine to do as long as you know that you have a CD drive and will be able to easily read data from that. And just avoid things like floppy disks or any form of data or any form of media that you don't have ready access to if you do need to be able to recover it. Another thing to consider here is the role of cloud storage. UK provides storage via OneDrive, which can be very convenient because it allows for syncing between the files on your computer and files in the cloud. That can be a convenient and sort of lightweight option of making sure you've got another copy of your data. Just keep in mind that that isn't a true second version of your data because those files remain linked. So if there were file corruption in one place, then it would be synced to the other location as well, which would potentially keep you from being able to access that data. So if it's something that's convenient for you, it certainly can be a part of your backup strategy, but be wary of relying on it in totality. So when it comes to thinking about data backups, the overall advice that I have is just know who you're going to call. Ask yourself the question, if you try going to access your data tomorrow and suddenly it's all gone, who's going to be the first person or group that you reach out to? Maybe it's someone from departmental IT if you have it stored on a department server. Maybe it's the customer service for whatever company it is you're using for data storage there. Maybe it's UK ITS if you have your data backed up using the data protection service, for example. I'm not saying that these data backup policies are something that you need to understand and think about and really work into your research process every single day that you're doing your research. But I do think that it's a very useful exercise to just sort of go through, ask some questions, poke around, figure out who it is that you would need to contact so that you can know what your plan would be if you do face this kind of data Armageddon. Another thing to consider is something like one of those external hard drives as a way of making sure you have a local backup of your data. Then even if you are using something like third-party data storage, you have access to all of your most important files locally in a way where you don't need to reach out to or contact anyone. You have full control over being able to access those. All right. And the last trope that we're going to talk about today is attack of the dataset clones. And by this, I mean data duplication, which can occur at a few different steps in the research process. During research itself, you may end up with duplicate observations in a spreadsheet or other tabular data file, for example, or maybe you end up with multiple images that are supposed to represent different I don't know, tumors, biopsies, different medical images, but are actually sheer duplicates of each other, which isn't something you can easily tell if you don't have those images side by side. So this can occur if you don't properly version your files to make it clear when something is another version of a previous data file. Or if you're combining data sets, maybe for data collection, you saved everything as a separate file, but now you need to bring them all together into a single data set. If you're manually copying those using something like Microsoft Excel, if a lot of different members of your research team are doing that, maybe two people accidentally copy the same files in, for example, and don't realize it. So those are just a couple of the ways that data duplication can occur during research, but it can occur with data reuse as well. So some fields where data sharing is already quite common might have gold standard data sets that they use for various forms of analysis or testing out new methods. Um, but some of those data sets might actually contain the same data, have the same observations listed in there multiple times. And so if you aren't carefully vetting the data that you have, you might end up in a situation where you have duplicate data in there without even realizing it. And I'll go into an example of that in a little bit more detail. But first, this will be an example involving machine learning. So I want to just give sort of a quick, very high level overview of what supervised learning looks like in a classification problem, for example. And so the basics of supervised learning are we start with a data set, we have a series of observations that are all structured in the same way or similarly. And then we have some method that we're going to want to use to predict some feature of that data set. Um, in order to do that, once we have our method, or rather to test the efficacy of whatever algorithm or other method we come up with, we'll need to split that data into two categories. One will be training data represented here with these white squares, and then one would be testing data with these purple squares. Then once we have our model, our algorithm, whatever it may be, we test it by, or we train it by having it look only at the training data and look for any commonalities in that data to be able to figure out what's the relationship between variable A and variable B at predicting variable C. And then when we want to figure out how effective that model is, we would then show that model the testing data which it hasn't seen before, and see how well it can predict that variable C if we give it just variable A and variable B. Um, the crucial thing when it comes to this kind of supervised learning is that our model has never been exposed to any of the observations that are included in the testing data set. If it has been, if those test examples are included in the training data, then kind of intuitively, that's going to make it a lot easier for our model to correctly predict some feature of that because of that testing example, because it's already seen the exact same example in the training data. So all of this came up in several different studies in metabolomics research that was trying to look at different metabolite pathway relationships. And there were a number of different gold standard metabolite pathway data sets that were already out there. And so it was a common practice for researchers who were trying to develop methods for predicting new pathways to combine multiple of those data sets in order to be able to figure out how good their new method was at making predictions. The problem was a number of those data sets were actually based on the same underlying data. And what that meant was that when researchers combined that data and then split it into training and testing sets, because there were duplicate occurrences of that data, there were some observations that ended up both in the training set and then in the testing set as well, represented by these little purple squares. And what that means is that there were these models that were having performance indicators that were suggesting that they were more accurate than they actually were because the model was getting a chance to see an exact duplicate of this data first. So there was a study that was done by one of UK's own researchers, Hunter Mosley, that reviewed a number of different studies that tried out some of these metabolite pathway prediction models and looked at the underlying data that they provided and found that this data duplication was going on. And what that meant was that all of these models were predicting higher levels of accuracy than they should have actually been able to do, or than the models actually were. Um, and the study, which I've linked to here as well, is actually a very interesting one, in part because they go and break down what research, or they break down which studies share their data and which ones don't. They had good reason to suspect that some researchers who weren't sharing their data did have this data duplication process, but it was difficult to be able to tell for sure because their data wasn't being shared. There were other researchers who did share the data sets that they used, which meant that Huckvale and Mosley were able to go through and verify that these duplicates did actually exist, and then rerun the analysis to be able to produce new performance statistics for those models. And so this is kind of a cautionary tale, not just about data duplication, but about data sharing as well. Those researchers that did share their data, even though it did expose this problem, it meant that new researchers were able to attach specific numbers to how that changed their findings. Whereas those researchers who didn't share their data, there were now these potential issues that were known with their findings, but there was no easy way to quantify that or be able to tell for sure what was going on because those other research products weren't being shared. So I know that was kind of a long example, but it's one that I really find to be very interesting and I think illustrative of where these types of data duplication problems can happen and then how we can respond to them. And there are a couple of different ways you can make sure duplication doesn't happen during the research process itself. One of those is to practice version control to make sure that you can clearly tell the difference between different iterations of your files. This can be something that you integrate into a file naming convention and can be as simple as just adding on a piece of information at the end of the file name with a version number written here as V01. We start with that leading zero just as a way to make sure that we can more easily sort these, because otherwise a computer will sort V1 as coming before V11 followed by V12. That leading zero is just important for helping with that automated sorting. If you don't want to use just those version numbers, you can also use more description version names as well. So a common example here would be to save a copy of your raw data file directly as that's been observed, as it's come off the instrument, whatever it may be, and then having another version for that analyzed data or that cleaned or otherwise processed data, and then having another version that you save for what's published as well, so that you can easily go back and verify what's been shared with other researchers. If those names are clearer for you than using version numbers, that's perfectly fine to do. But again, coming back to this common theme, just make sure that the meaning of those is documented and that it's consistently applied. So make sure that if you're saying your files are analyzed, make sure that means you've taken the same data cleaning steps for each of those files so that you and other members of your research team can have certainty about what that data represents. Another thing to consider, like that case I was talking about earlier, where maybe you've collected data in different files, but then you're combining them into a single file. Maybe you had a piece of information, such as a study site or a date of data collection, that was present in the file name, but didn't have its own variable in the data set itself because it was already in the file name. What that means is that when you combine different files, make sure that any information that's reflected in the title or anywhere else has its own column or has its own variable in whatever new data you compile as a way of making sure that you can check and verify for duplicates. So in this example here, we have two different files for study sites 1 and 2. And then when those are combined into a single file, we've added an extra variable for site here. This means that if we ever need to go back and check, hey, did we actually include the data for study site 1 here? We can go and verify that it has in fact been included because we can see that variable represented in the data. And then the last thing to consider here is try to use software tools whenever possible that make it easier to track any changes that you've made to your data. This looks very different from one discipline to another and from one method to another. But one example that I hope is sort of broadly applicable is thinking about how we would handle something like outlier data in a tabular data set in, let's say, Excel. So in Excel, we have a point and click interface there. If we want to remove outlier data, then we could start by just sorting all of the file or all of the rows by their target variable. We could delete any rows that meet our outlier criteria, so maybe are above a certain threshold. And then we could save that new clean data file without the outliers as a new file. There are other ways that we could get fancier with this. Maybe we could apply filtering instead, and that would sort of document some of what we're doing, but it still wouldn't be easy for someone to go and open your data file and understand what values got dropped here. And that can be important because maybe there's another researcher or member of your research team who disagrees with your outlier criteria. Maybe they want to tweak it a little bit and it results in very different results. So making sure that those steps for data cleaning are actually recorded is really important. Maybe that's something we can include in a methodology section or in a README file if we're doing that data cleaning in Excel. But whenever possible, I encourage researchers to try using tools that will do this more automatically. And one way to do that is, if you're comfortable with it, interact with your data in a scripting-based environment. So using a coding language like R or Python. And if we compare the steps for removing outliers there, we would load the data into whatever environment we're using. We would write code that deletes any rows that meets our outlier criteria. And then we would save both a clean version of our data as well as the code that we used. That code is then step-by-step instructions on exactly how it is that we've changed our data, which are easily available to anyone else to see and tweak as is necessary. So if you're interested in learning how to interact with your data in that environment, I encourage you to check out our library services. We have a data applications librarian who offers training and instruction in using R, and I can provide assistance in working with Python as well. So we can help you get started if this is something that you think might be applicable to your data, but you will want to have a conversation about it first to figure out if you want to dig deeper into it. Oh, and then the last thing I'll mention is when it comes to reusing data from another research team, such as thinking about some of those gold standard data sets, just make sure that you're carefully reviewing how that data is collected to understand what its source is, to be able to confirm that it's valid for whatever purpose you're putting it to. Make sure that you read any accompanying documentation with it to make sure that you're interpreting the data and all of the variables there correctly. And then do perform a manual check for any duplicates, whether that's combining all of the data into a single file and sorting by different variables that you think might indicate duplicate data values. And then also, when you are working with different data sets, consider any other potentially statistically confounding factors as well. Maybe these data sets were collected by independent research teams, but maybe they were collected at the same study site during the same time period, which would sort of challenge your ability to treat them as independent or random observations if there are some confounding factors there. So those are some things to consider when you're reusing data that others have collected. So in thinking about how you can apply these to all of these issues that we've talked about today to your own research practices, I encourage you to think about which of these movies sounded the scariest to you, and then take that as a jumping off point to focus on where you will want to improve your own practices. If you find that you're losing your files very frequently, try developing a file naming convention. If you're working with other members of a research team and there's often confusion around data management policies, try working with that checklist to develop some new ones. If you really aren't sure who you would contact if your data suddenly disappeared someday, to spend some time investigating how your data is being backed up and maybe create some new ones if that's something that you need. And then finally, if you are working with combining a lot of different data files, especially if you're doing that manually, then think about some ways to keep track of the different versions of your files, document changes to them, and review any data that you're reusing. If you want to get any help with dealing with any of these issues, then I highly encourage you to check out Digital Scholarship and Data with UK libraries. I, as the research data librarian, can help talk to you about implementing any of these practices, as well as other good data management practices throughout the research data lifecycle, and recommend tools that can help you with these as well. Additionally, our data applications librarian, Diane Parr, can help you with dealing with some of these data cleaning and data duplication issues within the analysis process itself. So she can be a particularly good resource if you want to work with your data in R, but she works in other environments as well and can help you get started in figuring out what tools are the best for you and then identifying some resources for working with them. So that's all of the information that I have for you today. I hope that you've all enjoyed our tour through the data management horror movie canon. I hope that you spend some time thinking about some of these and how you would be able to survive them if you end up in them. And I thank you very much for joining us today. And please feel free to add any questions into the chat or come on mic if you'd like to ask them there. Additionally, Laura just shared a link to a feedback survey as well. If you can fill that out, that's very helpful for us for assessing our services. And then I'll also note that if you registered for this, then you'll receive an email afterwards with a link to the recording and slides as well. So if you missed any of these links, you can get access to them. So there's a question about groups storing documents in SharePoint or a Microsoft Teams shared folder. Is that acceptable as a storage location? Um, I would say when it comes to those Microsoft products, so SharePoint, Teams, OneDrive, they can be a good option because they are convenient for a lot of people. But there are some issues you can run into with them. So for example, if you have a team on Microsoft, or if you have a Microsoft Teams that you don't interact with over the course of a year, then that team and all files that will be associated with it automatically get deleted. So you would need to make sure that you're actively managing that and checking up on it and interacting with it to keep that from happening. The same can be the case with SharePoint. I'm not sure if SharePoint sites are automatically deleted. I think UK ITS does do some sort of cleanup for them. Those can be helpful for sort of setting up like an internal research page for being able to manage a lab and have people add data to them. So they can be good for thinking about actively managed research data, but I do recommend building into your research practice regularly downloading a copy of that data to something like an external hard drive or a local machine, just because you never know when something is going to go wrong at Microsoft or someone's computer gets infected with a virus, for example, and then goes through and automatically deletes everything that it can on their machine. So all that's to say that those Microsoft products really do have a lot to offer, I think, in terms of convenience. But like I said, don't outsource 100% of your thinking about data backups to 100% of your data backups to those services. And then we also have a question on for data that's saved using applications like RedCap, is that data saved on a server on site here at UK? I believe the answer to that is yes. And if any of my colleagues from the Medical Center Library know for sure, please, yeah, thanks, Celine, for sharing. Yeah, that we do have a local RedCap instance here at UK. I believe that's also for HIPAA purposes as well to make sure that that data isn't leaving UK. One area that I didn't touch here as much is thinking about if you do have data that's personally identifiable or is otherwise covered by HIPAA, then you do want to be careful about saving that data in a lot of different locations because it leads to some of those potential data leakage issues that we discussed. There are some options for addressing that. One would be, I believe our local RedCap instance does have its own backup. So that's something that you can investigate to sort of ask questions about, what happens, how is that data being secured to make sure that there's not just one copy of it. Another thing that you can do is have a separate file for any identifiable information. So for example, any of those HIPAA fields, personal addresses, birthdays, etc., stored in a single file with a randomized key, like a participant ID stored in that file as well. And then make copies of your data that don't include any of that PII in them or any of that HIPAA covered information. That can be a way of making sure you're getting some of those backups. But that is a process that can take more time to be able to implement. But those are just some of the things that come with handling human subject data. And we're almost at 1 o'clock, so I won't keep anyone longer than we need to. So thank you again very much for joining us today. Please do fill out that survey, set up a consultation with me if you'd like to discuss implementing any of these practices personally. And I'll also be staying on for a little bit afterwards. So if you have a quick question that you want to ask, but just don't want to put in the chat, then feel free to stick around and we can talk there as well too.